talking about query content in sequential one-shot multi-agent limited inquiries when communicating ad hoc teamwork. I'd like to first really quickly thank my collaborators, namely Reuth Mirsky and Peter Stone, as well as the UT Austin Learning Agents Research Group for letting me be here to discuss this research. So I'd like to start with a very quick definition of what we mean when we say ad hoc teamwork. So ad hoc teamwork is basically any multi-agent task. We have agents that need to collaborate with each other without having interacted in the past. So you can think of some common examples are if they're disaster recovery. So there's been some sort of natural disaster like a tornado or an earthquake, and we're deploying autonomous agents to try to assist with the recovery effort. And we don't have time to create collaboration protocols ahead of time because time is of the essence and we need to move now. Or a more abstract example is drop-in soccer, where you have a team of people that you've thrown into a soccer ring and they need to play soccer with each other, but they haven't played with each other ahead of time. So naturally, this requires a fair amount of reasoning and reacting to your teammates' policies and plans and planning accordingly. So as far as related work, there's been a large amount of work in ad hoc teamwork and also plenty of work in communication, focusing on sharing information. However, very little work actually considers what happens when you combine these and leverage communication and ad hoc teamwork. The reason being is that doing so requires the assumption of a communication channel, which other current ad hoc teamwork methods did not make. However, it's not unreasonable to make such an assumption. For instance, humans, when we meet new individuals, are regularly able to communicate with each other. And the reason being is that communication protocols and languages are generally common amongst many different individuals and not specific to pairs of individuals or two individuals together. Furthermore, some very preliminary work in communication and ad hoc teamwork has shown that including communication allows for better coordination between these agents and can increase improvements. So the specific form of communication we're going to be considering in our work is querying, where one agent can request information for another. And there are a few reasons why we chose this form of communication. First, queries are very structured. So it's a very nice form of communication where I ask for information and I get a response. So it's not a free form where you have messages constantly being passed. In addition, I can get information and improvement even if my teammate doesn't actually use any information passed by the communication. The only assumption we need is that they're able to respond. We don't need any assumptions about the teammate being able to infer things from my queries or to be able to query itself. So the then specific scenario in communication ad hoc teamwork we're going to focus on is a fairly simple one. It's where you have a fully observable deterministic environment. We say the simulations are one shot, meaning each game you play with an agent, you only play with that other agent once. So there's no repeated replay and you cannot learn a policy over time. We assume the teammates are optimal and that they are not adaptable, meaning that the teammates don't change their policies based on our behavior. So for instance, if you have in the soccer domain, a teammate that's aggressive and always tries to go for the score itself, it's not going to spontaneously learn to pass if we're also aggressive and only go for the score ourselves. It's up to us to determine that and learn to pass to that teammate. And finally, again, the communication we consider is where our ad hoc agent that we can control can query the teammate. We assume that the queries and responses are all noiseless. So there's no miscommunication or anything like that. And furthermore, because we're in a collaborative setting, we don't assume any sort of adversarial communication. The teammate has no reason not to be honest with us. And so we name this particular scenario the sequential one-shot multi-agent limited and ad hoc teamwork, or SOMALI CAT. The specific domain now that we're working with is the tool fetching domain. I have two instances of the tool fetching domain shown up here. The first is a small scale instance that's meant to be a running example for intuition on the left, And on the right, we have a much larger scale instance that shows like what we're actually going to be running in our experiments. So the tool fetching domain consists of two agents. The worker, which is the teammate in the scenario, is and shown by the gray circle with the W up here, is attempting to go to one of these three workstations, shown by the black boxes with numbers, and do some sort of task. However, whatever task it's performing, it requires some sort of tool to perform. And furthermore, the tool that it needs is going to be dependent on which workstation it heads to. So each workstation requires a unique tool. That's where it comes into the second agent, the ad hoc agent, which we control, also known as the fetcher, which is shown by the gray circle with an F. The fetcher's goal is to head to the toolbox, which has all of the tools, grab the correct tool, and then meet the worker at its goal station. The caveat, though, is that the fetcher doesn't know what the worker's goal is ahead of time, meaning the fetcher has to determine what the worker's goal is based on either its actions, or it can also query the worker for information. The queries that we considered were of the form, is your goal one of? So I could ask, is your goal either station 1 or station 2? And if the worker's goal was station 2, I would get a response back yes. And if it was station 3, I would get a response back no. The reason why we chose this form of queries is that this is very representative of many different actual queries you can ask in life. So the fetcher might ask the worker, is your goal above or below it? In which case is the same thing as asking, is your goal either station 2 or station 3? Or the worker might ask, is your goal number less than 3, which is the same thing as asking, is your goal station 1 or station 2? So you can see that these form of queries map into many different actual queries that we might be able to ask. So we consider this system just to be general. So the first question that we want to address in this, looking into this, is if I have a query, should I ask that query? And if so, when should I ask it? So to answer this question, we've created a few formalized concepts, the first of which is the zone of information. So very simply, the zone of information is the time period when the ad hoc agent can gain information from a query. So this is based on worst case distinctiveness by Sarah Karen et al., which is basically given two goals, the maximal amount of time when before a plan to these two goals can diverge. And so then the zone of information just maps into the time period that's less than the worst case distinctiveness of the teammate or the worker in this instance. So you can see if the worker follows this green path outlined by the circles here, we aren't guaranteed to know whether it's going to station 1 or station 2 up until the end of this path, when it has to either move up or down, depending on what its goal is, at which point we are guaranteed to know. But prior to that, we may not. The second concept is the zone of planned branching. So this is the time period where the ad hoc agent's plans can diverge or branch from each other. So this is similarly calculated, again, using worst case distinctiveness, but this time using the worst case distinctiveness of the ad hoc agent or the fetcher in the tool fetching domain, which in our case corresponds to the toolbox, because in this example, because every plan, regardless of what the worker's goal is, the fetcher always wants to head to the toolbox. And it's only when the fetcher arrives at the toolbox that it then needs to make its determination about what tool to grab and which station to head to. And I again have the portion of the zone of planned branching of the worker's plan if it was heading to station 2, shown by the blue circles in the figure at the right. So then putting these two concepts together, we arrive at our finalized concept, which is the zone of querying. Now, this is the time period when the ad hoc agent can actually gain value from asking a query. Fairly intuitively, it's the intersection of the zone of information and the zone of planned branching, and it has a few nice properties. First, if the zone of querying is empty, I'm guaranteed that I cannot get any value from the query. It does not have any benefit of me to ever ask that query under any circumstances. Second, we have this concept, the critical querying point, which is the beginning of the zone of querying, and we can demonstrate that this is actually the optimal time to ask a given query. So just a quick example to give you some intuition. We have the fetcher following and worker following these paths. So we're currently in the zone of information, but not the zone of querying, because we're heading to the toolbox. then the moment we get to the toolbox, we now need to make a determination about which plan we're going to take. So we enter the zone of querying because we don't know what we're doing, what we should be doing. And then once the worker disambiguates between these two goals 1 or 2, we exit the zone of querying, and now we can no longer get value from the query because we already know the information. And for more information on this, you can see our Ichikai submission, Penny for Your Thoughts, Value in Communication and Ad Hoc Teamwork. So these give you a very nice principled way to determine when you should query and what you should, and if you should query it at all. But it doesn't actually answer the question, if I have multiple queries I could ask, which one of these should I ask? Now, a very simple heuristic you might imagine is I'm at a zone of querying. I don't know what the true goal is, so I'm going to ask about half of the potential goals at random and effectively do a binary search until I know what I can do next. However, this can give suboptimal behavior. So consider the example on the right. It's slightly modified, only now we've taken the tool for workstation 1 and moved it up here, while the tools for workstation 2 and 3 still remain at the bottom location here. Now, as you can imagine, I'm going along this path. I arrive at tool station 1. I now don't know what I should do next, so I've reached a zone of querying. I can either grab the tool for 1 and head to workstation 1, or if the worker's goal is either 2 or 3, I should head down to stations 2 and 3, or the tool for station 2 and 3, and then make a further determination when I arrive there. So again, if we were to use the simple heuristic, we could ask about half the goals randomly, and this might produce the query, is your goal either station 1 or station 2? And this is not a good query to ask in this case, because if I get the answer back yes, I still don't know what I should do. If the goal is station 1, I should head to station 1, but if it's 2, I should head downwards. So I need to ask an additional query then. However, if I were to ask, is your goal in station 2 or station 3, this guarantee is to give me the information that I need to know how to act optimally, regardless of what the response is. And the reason for this basically is that there's now multiple zones of plan branching, where there's one zone of plan branching for workstation 1 with everything, and an additional zone of plan branching between workstations 2 and 3, as shown. And asking about 2 and 3 then aligns our information with the second zone of plan branching if we get the answer back yes. And again, we can guarantee to know how to act in that time step. But there are other additional factors that could complicate things. So say, for instance, there's some sort of non-uniform probability distribution over the goals. So in this case, the worker is far more likely, 99% of the time, is going to head to workstation 3. It actually may be better in this case to not query at all, and then just to head directly to the tool for station 3 and assume, unless I see some sort of evidence otherwise, that 3 is the worker's goal. And we can even further complicate this by assuming that there's different costs to different queries. So I want you to, again, consider a very simple query cost model where you have a base cost, or the cost of initiating a query. You would incur this whenever you ask a query, regardless of which query you ask. And then a per station cost, which is the cost of including a station in the query. So again, back to the previous example, if I were to ask, is your goal station 2 or station 3? That would give base cost plus 2 times the per station cost. Now, when we introduce this new cost model, is your goal station 2 or station 3, when we arrive at this toolbox at tool station 1, is no longer an optimal query to ask. For the simple reason being that I can get equivalent information by asking, is your goal station 1? And this only incurs the per station cost once. So this is another factor we might need to take into account. So to solve these complications, we introduce a series of heuristics. I have here, again, the representative example of the experiments we'll be running at the top here. So the first is a heuristic where we're focusing on minimizing wait time. So I'm going to ask queries to try to minimize the amount of time before I know an optimal action in the next time step. And I have here on the right a corresponding formula for this. We optimize these formulas using an integer linear program. I unfortunately don't have time to get into the specifics of what these formulas mean, but they're in the paper and I'd be happy to discuss them with anyone after the fact. So that's the first heuristic, is just minimize the wait time until we know how to act optimally. The second is to actually do something very similar, but to actually weight by the goal probabilities of the stations. So basically try to query about stations that are more likely, so that we are more likely to get an answer yes, and increase the probability that we're able to know an optimal action sooner. And the third is similar, but simultaneously we incorporate the query cost into the model. So we're trying to simultaneously maximize this objective while minimizing the query's cost. So our experimental setup, we're working with tool fetching domains and a grid size of 50 by 50. There are 100 workstations scattered randomly throughout this grid world, as shown by the black boxes here. All physical actions, so moving up, down, left, or right, or waiting, have a cost of 1. And there are 5 toolbox locations also scattered randomly throughout the tool fetching domain. So we worked with different probability distributions. We assumed there was a base cost of querying of 0.5, so half a physical action you incur for every scenario. And then we investigated different scenarios with different per station costs of the cost model discussed before. So I have here some of our first results. So this is a figure showing the y-axis, the mean marginal cost. So this is the cost over an optimal plan if we were to assume the fetcher knew the worker's goal at the beginning of the simulation. So it's how much worse we're doing than the hypothetical best. And then on the x-axis, I have the per station cost, which is ranging from 0 to 0.5. Again, that's the cost that we incur for including a station in a query. This blue line here shows the mean marginal cost of the never query strategy, which is when I don't know how to act optimally, I just wait until I wait until I'm guaranteed, until I do know the worker's goals or it's been disambiguated based on the worker's actions. And you can see here, the performance of this doesn't really change a whole lot with the per station cost. It's pretty static around 30, which is to be expected since this strategy doesn't ask any queries. So our first heuristic that we looked at is our random query baseline that I discussed in the beginning, that queries about half the possible goals randomly. And you can see for low per station cost, this is able to do substantially better than the never query strategy, but increases very, very quickly as queries become more expensive. And by the end is actually doing worse than just not querying at all. When we introduce our first heuristic, you can see it's doing a fair amount better. It's still, again, doing significantly worse at the end, but it increases much more slowly and does significantly better than the random query baseline. When we weight by goal probability distribution, it doesn't actually do a whole lot better, but again, that's to be expected considering, oh, apologies. So in this case, the worker's goal is chosen uniformly at random from amongst all the workstations. So it's a uniform probability over the stations. And so again, because when we're weighting by goal probability, we're not actually gaining any additional information. So this is not too surprising. But then when we include minimizing query cost, you can see we actually then get a further improvement over the minimized wait time heuristic. Furthermore, we can use a paired t-test and demonstrate that from query costs from 0.1 to 0.4, the minimized query cost heuristic does significantly better than every other strategy here. And it does significantly better at every strategy when the cost is 0.5, except for never query, which it does comparable to. And in the actual paper, we also discussed additional probability distributions, but I unfortunately don't have time to discuss those today. So a quick summary of our work. We extended our existing work on the Somali CAT scenario with different zones of branching, goal probability distributions, and query cost models. And we developed several querying policies and heuristics to try to solve those generalizations. Finally, we demonstrate that the value we can get from communication is substantially dependent on what we're querying, in addition to the timing of when we're asking it. So a brief summary of then our ongoing research of directions we're pursuing. The first thing we're looking at is developing a general definition for the value of a query in any SOMALI CAT domain. And we want to then use this as our new objective to optimize rather than the existing heuristics. We want to run experiments with our algorithm and these heuristics in other SOMALI CAT domains besides the tool fetching domain, so showing some generalization. And finally, we're working on actually running some human-in-the-loop experiments to see how these strategies perform when there's an actual human controlling the worker, rather than the simple plan error that we're using right now. So thank you. Are there any questions?